All right, so this is Module 5, and the purpose of this module is really just to take a step back and use what we've learned in the previous 4 modules to write some more realistic programs and to solve some larger problems. Specifically, what we're going to be dealing with is variables, but the thing that we're going to be practicing the most is figuring out how to get this dialogue with the user correct. There's lots of technical aspects of this, thinking about making sure that you have read your variables from the user before they become parts of equations and before you actually try to start calculating things, but also learning how to ask the user the right questions and how to present your prompts correctly to the user. We'll need to think about units of measure. We'll need to think about how we want to explain to the user what it is that we're really expecting them to enter. Part of the process of becoming a good programmer is not just learning C++, not just learning the tools, but also being able to put yourself in a position of a user of your program. Ultimately, your users of your programs don't look at your source code. So you need to be very clear when prompting them and when talking to them through your program, what it is that you're doing and what it is that you expect. Another thing that we're going to do with these examples today, or with this module, is draw a few diagrams and draw a few flowcharts. We're starting very simple. We've got very easy, or what will later appear very easy problems that we're going to be solving. But it's important to get into some good habits, and the number one habit here is to not start writing code immediately. Whenever we're presented with a programming problem, we want to take a step back and we want to think about, well, what are our inputs? How are we going to actually calculate our outputs? Sometimes you'll be given real equations. Sometimes you're going to have to think about it a little bit more. So it's always best to start by writing some stuff down, writing a plan down, and thinking through the steps that your programs are going to take to come up with their answers before just trying to solve the problem in C++. So what you want to keep in mind is that you're learning C++, you're learning a completely new language, you're learning how to think like a computer to some extent, but you're also being asked to solve problems that might look like word problems on a math test. So you're going to have to make a choice. Do you want to try to think and solve these problems in a brand new language, or do you want to think and solve these problems ahead of time, figure out a plan using diagrams, using plain English, and then just simply translate that to code? And the second solution tends to be the easiest one. So let's start with programming example 3. And for this example, we're going to calculate the cost that it takes to ship an individual item. And the problem states that ultimately the amount of money that you're going to pay to ship an item is going to be determined on a fixed rate of $2.50 per pound per 200 miles shipped. So to be able to figure out how much something's going to cost to ship, you need to know how many miles you're actually going to ship it. So for instance, if it's 800 miles, it's going to be 4 times whatever this $2.50 per pound ends up being. And you're also going to have to know the weight of the item that you're going to ship. Of course, if it's 2 pounds, then it's going to be $5 per 200 miles. And then at the end, we're going to output the total cost. So let's start just by diagramming this out and thinking about, well, what are the variables that are going to be involved? What are their data types? Where are they coming from? Remember that we also need to think ahead of time, what kind of data, what data types are we going to use? So if we think about what are the pieces of data that we're going to have to deal with, we can start out with, sure, cost, right? We know that that's ultimately the biggie that we want to be able to calculate. We can write down what it is. It's the output. We can say it's the result of a calculation. And we should also think about the data type. And so the cost is a numeric value, obviously. It's also a fractional value. It's money. So there's going to be dollars and cents involved. So we can do a float or a double. would make sense here. The other piece of information we need to know is distance. And this is going to be an input from the user, and it's going to be in miles, which could be 1.5 miles, so certainly we would want something like a double. And we want weight, which again is an input, and it's in pounds, and it's in a double. So we ask ourselves, of these three variables, where are they coming from? Two are inputs. One is an output, a result of a calculation. All three of them are going to be of type double. So step one in our program is get input, which is going to be prompts. Step two is calculate cost. And step three is going to be output. Now there is some hidden complexity or hidden importance in these prompts. Notice that we're specifically assuming, based on our equation, and we'll get to that in a moment, we're specifically assuming that the distance and the weight are measured in miles and pounds. And that's because our calculation, or our equation here, is $2.50 per pound per 200 miles. Now the user doesn't actually see this formula, right? We know that this is going to be involved in the calculation of our cost. What the user needs to know, though, is that when they're entering their input, that distance and that weight has to be in these units of measure. And the only way that they're going to know that is if that's in the prompt. Right? So we need to be clear about that. We also, when we output the results, well, we need to make sure that it's clear that that's dollars and cents. Now for this particular problem, I'm not going to worry about numerical precision. So if I print out, a dollar 1.235 as the cost, we'll let that go, and we'll come back to input formatting or output formatting later on in a future module. So now with our diagram, we've sketched out all the basics, and we've gotten a little bit more technical. We've got output, we've got input, we've got units of measure, and we've got data types. Now we can start moving to our program and start looking at this first step of getting all the inputs. So we'll start out by declaring our variables, and we've got distance, weight, and I'm just going to write down input just to remember where those things are coming from. We've got cost, which is a result. We don't write down the formula quite yet because we haven't gotten the input. And that 250, if we go back to the formula, that 250, we figure in this short program we probably won't type that multiple times, but that might be a good candidate for a constant. Maybe we can change that later on, and we can change it throughout our program. So I'm going to write down the 250 as basically cost per pound, and I'll make that a constant. And I'll just make it $2.50. It's fairly standard practice to make our constants all capitalized, separated with underscores, where regular variables are lowercase. All right, so first step, get your inputs. So please enter distance to ship. And I'll read in our distance. And, I'm gonna have a lot of stuff here. I'm gonna have a couple more inputs. I'm gonna have a calculation, but eventually we'll print out the final data. And I always like to include a summary of my inputs. So I'm gonna print out that dollar, or I'm sorry, just the distance. And again, this is summary data that would happen at the very end. I probably also want to reiterate that it's miles, and I say reiterate, but I haven't actually explained to the user yet that that is supposed to be miles. So first, let's just run this, and we'll see the immediate value of having, reading in the data and then printing out the results. And again, we've got unreferenced local variable warnings because we haven't made use of the other inputs and outputs. So let's type in PO3. Whoops. I think I named it PE3, sorry. And we'll say the distance to ship is 500. So the first thing you see that comes out here is the shipping distance is 500 miles. And so when a user runs this program, the first time they run it, if they typed in 500 and they see 500 miles come out, they immediately realize that, okay, well, the program was asking for miles. But they shouldn't be made to wait until after they type in the value to see that that number is going to be interpreted as miles. If they typed in 500 thinking it was kilometers, they're going to get a wrong price. And if they're not careful, they might not actually even catch this. Now, just looking at this input prompt, of course, we haven't said what kind of units we want, but we're ready to read in a value. Remember that the cout statement prints out all of this text and then stops. I did not have an end of line. And the cin statement is causing this blinking light. So printing out the word miles, like after the cin or something like that, won't work. So I'm going to have to include it somewhere in this string. There's nothing we can do to force the user to type in miles, right? If they type in a value thinking that it's in kilometers, there's nothing we really can do about that. The best that we can do as a programmer is to make it very, very clear in the input prompt, and then, frankly, hope that the user reads that. So I'm going to hit Control-C, and of course I get some garbage data print out as a shipping distance. But let's adjust this prompt. And we're just going to include the units of measure there. Now when I print this out, please enter the distance to ship in miles. Again, the user hopefully has read that. They'll understand it. They'll type in 500, and it won't be a surprise when the output comes back as 500 miles. So let's get the other inputs. Just weight. And again, pounds. It's important that the user realizes that it's not in kilograms, it's not in tons or anything like that. All right, we'll read that data in. Might as well just print out our results as well. Shipping weight. I generally try to line up my spaces here a bit. I'll print out weight and definitely print out my units. So 400 miles, 12 pounds, and we can see 400 miles, 12 pounds come out. So if we look back at our initial workflow, we have, switch over here. We've declared our variables. Let's put a big check here. We've declared our variables. We've declared cost, but we haven't calculated it yet. And now we've gotten our inputs. And now we're ready to do the cost calculation. So let's assume first off, let's forget about distance. All right, if we have something that is 5 pounds, or I'm sorry, that's 5 pounds, let's say, it should be 2.50 times 5 to ship it 200 miles. So if it's a pound, it should be $2.50 to ship it 200 miles. So let's just write that equation in, or write that formula in. And I'm going to use a temporary variable. because it's not the ultimate cost. So I'm gonna, right after I get distance and weight, I'm gonna start my calculation, and I'm gonna just say cost for 200 miles. And that is equal to, so if it's $2.50 per pound, then the total cost is cost per pound times weight. And I can actually print that out temporarily. And I'll put a $ at the end so it comes out looking like money. And I'll have cost 200. So I might not have that actual value printed out later on when I'm done with the program, but for now I'm just gonna print it out. So if I've got 400 miles, that's really irrelevant right now. Let's say I've got 3 pounds. We can see that it's $7.50 per 200 miles, which is accurate. It's $2.50 times 3 because I've got 3 pounds. So working our way back here, what we've done now is we've done this portion, and we've saved that into cost 200. And I keep going back to drawing this out, and I would encourage you, as you're learning here, you can eventually start to skip these steps a little bit probably as you get better. But as you're learning how to do this, keep that paper in front of you and keep writing and adding notes so you know where you are and you can stop and you can come back to the program later on. Now we'll go back into the source code. And if the user is going to ship 3 pounds, it's going to cost them $750 per 200 miles. But if they want to ship 600 miles, then it's going to cost them, $7.50. Then it's going to cost $7.50 times 3 because 600 miles divides into 200 miles 3 times. Right? So we need that calculation as well. So we've got cost equaling the cost for 200 miles times the actual number of miles that they've gone, 200, divided by that initial 200 mile value. And in fact, that's probably a decent constant as well. So const, let's call it mileage baseline is 200 miles. So our baseline is 200 miles. If we want to ship 500 miles, then it's the cost per 200 miles times the 500 divided by 200. And let's put that out here. And again, I'm going to end with a $, so the dollars and cents shows up right next to it. And we'll just put cost. So let's say we've got, let's say we're going to ship 2 pounds. Oops, I wrote the wrong input there. We're going to ship 600 miles, 2 pounds. Let's think about, will these numbers make sense? So the cost for 200 miles was $5. We're probably going to remove that, but that does make some sense because we've got 2 pounds. It's $2.50 per pound per 200 miles. So it's $5 to ship 200 miles. I'm asking to ship this 600 miles. So 600 divided by 200, the baseline mileage is 3, and we've multiplied by 3 and we get $15. And certainly this will work in fractions as well. If we want to ship 305.5 miles and our item is 1.9 pounds, certainly we get a different value. We can see that the dollars and cents doesn't really print out quite accurately, or it's accurate, but it doesn't really look the way we're used to seeing dollars and cents. We'll learn about that later. And this is something that you'd want to check with a calculator and make sure that you double check all your numbers. So just pointing out a couple of the things, I've lined up all my inputs here. I probably want to get rid of this temporary one. Let's just get rid rid of that. I've used temporary variables to perhaps make the equation a little bit more straightforward. Whether it was easier for you to do without the temporary variables or not, it's really your preference. But we can see the output's nicely formatted. Our prompts have our correct units of measure, and then our display of the results echo the user's input and also has our units of measure as well. All right, so let's move on to programming example 4. It's going to be a similar type workflow where we're going to gather some inputs from the user and present some output. And we're again going to reinforce this notion of making sure that it's very clear to the user what kind of output or what kind of input, is being expected of them. So I'm going to ask the user for 2 inputs, just as before. We're going to have a base price of an item. So let's say you're going to buy something at a store. You've got a base price, it's $10, let's say. And we know that we're not going to actually pay $10 unless it's something like food or clothing. There's going to be sales tax on it. In the state of New Jersey, it's 7% sales tax. Obviously, other states have different rates, some have none. But we can calculate the total amount that you're going to pay by calculating the amount of tax and then adding that to the total, the actual price of the item. So I'm going to ask the user for 2 different pieces of information, base price and sales tax, and present that result. Where things are a little tricky, or something that we need to continue to think about, is how we're going to actually ask the user for the sales tax. So if I ask you how much is sales tax in New Jersey, you're probably going to just say 7%. We need to think about how to make that percent calculation. How do we use that percentage in actual calculations? So let's go back and diagram this out a bit first. So I'm going to start by writing down what I see as the variables. We have the pre-tax price, which certainly, since this is all money, these are going to be doubles. And that's an input. The user's going to have to say what the pre-tax, the initial price of the value is. We've got the sales tax rate, which is really a percentage, certainly should be a double, and it is an input as well. And then we have the final price. That's going to be a double. It's certainly dollars and cents. And it's a calculation and obviously an output. And so we need to think about the formula for this. So the formula, so let's say final price is equal to pre-tax, the $10, let's say, plus the amount of tax you're going to pay. Now, the amount of tax that you pay on something that's $10, if you've got a 7% sales tax, is going to be 70 cents. It's just going to be the pre-tax amount multiplied by the sales tax rate. You're going to take that total tax and add it to the pre-tax to get our final price. And in fact, we might actually end up using a temporary variable called tax as in our calculation. Step 1, inputs with prompts, and step 2, calcs, and step 3, output. Now, where the difficulty comes in is how we express this rate. So if something's $10 and our tax rate is 7%, we expect to pay 70 cents. But if we say 10 times 7 in terms of the sales tax, if the sales tax rate is 7, as in 7%, we're going to get $70 as the amount of tax, pre-tax $10 times 7. So certainly the 7% should not be represented as an actual whole number, as a full number like this, since $70 plus 10 would mean that you would pay $80 for a $10 item. It doesn't make any sense. So we know that the units here is percent. Now we don't have a data type for percentage. So instead, we're going to have the percent come in as a fraction. For 7%, it would be 0.07. And we're going to explicitly ask the user to type in 0.07 for 7% or 0.03 for 3%. We need to make that very clear to the user in our prompt, because if they do type 7 instead, our calculation is going to be pretty messed up. All right, so let's write our code. I'll create my variables, pre-tax. We'll do sales tax rate as rate, and we'll do final price. I'm going to prompt for some inputs. Please enter pre-tax cost, and I'll put a $sign right next to it so the user knows they got to type in dollars and cents. We'll ask them for the rate. And here we need to be very specific. So sometimes it helps to just write an example. 0.07 for 7%. The user's not going to type the percent sign either. At this point, we've done our first step, right? So we've declared our variables. We've completed the input section. We've got to do our calc. Final price equals pre-tax plus pre-tax times rate. And certainly we could have also written it as pre-tax times 1 plus the rate as well, if you want to factor it out that way. That's okay. Either way is fine. And at the end, we'll do our output. So pre-tax, always repeat the user's inputs. It'll help the user find their own mistakes if they mistype things. Sales tax rate, and here's where we can get a little clever, because what we can do is we can print out as the sort of human readable percentage. So if the user types in 0.07, I'm actually going to type it. I'm going to print out 7%. And I can do that by just saying rate times 100. And I'll put a percent sign right afterwards. And then I'll do final price. And let's line these dollar signs up. And we'll do a build. As for the pre-tax cost, and let's keep the number simple for now, $10. We'll type in 0.07. And we can see pre-tax cost is $7. Sales tax rate is 7%, and the final price is $10.70, and we don't have the numeric formatting quite yet. Now, let me point out the value of printing out sales tax rate as 7% here. It's very easy for a user to run your program, type in 40, see please enter sales tax, and not really pay attention to this part, or potentially maybe not even understand this part. So let's say they typed in 7. all right, because they know it's 7% sales tax in New Jersey. And I hit enter, and then all of a sudden they see this output of $320. Well, if they look at the output closely, they can see that I've interpreted that tax rate that they typed in as 700%. And with 700% sales tax on $40 would end up being really a final price of $320. So the fact that I've outputted the tax rate in a way that communicates to the user how I've interpreted their input, it's really valuable because it helps the user understand why that number might not be what they had expected. It'll cause them to look at that prompt a little bit more carefully next time. Now, if we wanted to be really nice for the user, we could actually allow them to type in 7 and convert that to 0.07. Right? So what we could do, instead of the way we have it right now, is we could read the rate in, and then once we read it in, divide it by 100. And we can do our combination here, or rate equals rate divided by 100. Now, if we did that, we probably want to change our input prompt, right? So let's tell them to type in 7 for 7%. And we want to change this as well. Well, actually, we'll have to keep that, right? Because once we enter in 7, we're dividing it, so the 7 will turn into a 0.07. So if we run this through, $10, I'm going to put 7 for 7% now, and I see pre-tax amount is $10, 7%, and $10.70. So I've read it in as a more natural number for the user, and behind the scenes, I've done the work to reconvert it to 100, or to dollars and cents, to percentage. Either way is acceptable. On an assignment, you might actually be asked, particularly allow them to type in 7 for 7% or 3 for 3%. Certainly, our program works with any percentage. If I rerun this again, $10, and let's say it's a 5% sales tax, certainly we see what 5% would be like. Sometimes the problem statement will be very explicit as to how the user should enter data, and other times you're going to have to think about that. Think about, from the perspective of the user, what would be most helpful. All right, so the last programming example for this module is switching gears a little bit and not paying as much attention, or not focusing quite as much on prompting the user and dealing with multiple inputs, but now getting multiple outputs, thinking about calculating multiple different answers. So what I want to do is write a program that can ask the user for a total number of cents. So maybe the user types in 702 cents for $7.02. And from that number of pennies, for instance, I'm going to compute how many quarters, dimes, nickels, and pennies should be used to create change in the most efficient way. The most efficient way being characterized by the fewest number of total coins. So rather than giving somebody 702 pennies, I would certainly break that down into giving them $7 worth of quarters and then 2 pennies. And so the problem statement is fairly simple. We're really only asking the user for a single integer value for the number of cents, but the calculation is a little bit less straightforward. So whenever we start a program, we want to think about diagramming out a strategy. This is one of those situations where the user inputs is a little bit more simple than the actual calculations. So let's say we start with an amount, which is an input, and it's an integer, right? So this is different than the previous examples where the user is going to type in, 762 for $7.62. So it's a total number of cents. Outputs are quarters, dimes, nickels, and pennies. And we need to figure out how to calculate this. Now, if the user, usually it's easiest to go by way of example. So let's do 767 cents. And let's think about how we're going to actually calculate. And I'm going to tackle quarters first. How many quarters goes into 767 cents? Well, if we take the 767 and we divide it by 25, we should get, I guess, 7 times 4, the 28 quarters. Okay, a total of 28 quarters. Now we have a remainder, right? So it would be dot, dot, dot. However, since this is integer division, and we probably should have wrote this as well, these are all ints. Since this is integer division, it's not going to have this trailing part. It's going to be exactly 28 quarters. So we can go ahead and sometimes it helps to sort of code a little bit and double check your calculations first and then actually rerun it. So let's do this first part first. We're going to ask the user for some input. We're going to figure out how many quarters they'll be given. So I ask the user for amount. Here's the amount. I'll have an output, and I'll declare them all here. And I'm just going to call them Q, D for dimes, nickels, and pennies. And we know that quarters is going to be equal to amount divided by 25. And I'll output the results. So let's run this and just double check that everything seems okay. I did not call amount A, so amount is amount. All right, and let's run this. So 767, whoops, there's a 767 quarters. That's not right. Looks like I printed out the wrong thing, actually. I don't want to print out amount. I want to print out Q for quarters. And we can see 30 quarters now. And I guess, oh, yeah, that's right. So $7 would have given us 28, but then, of course, the 67 will give us an extra 2 to make up $7.50. So let's go back and change that diagram. I wasn't really thinking about the 67. But 28 quarters will give us $7, the 700. 2 additional quarters will go into the 67, and that gives us the 30 quarters. Sorry about that. All right, so now the question is, well, how many dimes? How many dimes do we give as change? Now, the number of dimes, if we didn't have quarters, would just be 76 dimes, right? We would take the 767, we'd divide it by 10, and it'll give us 76 dimes, and then we could give a nickel and 2 pennies. But that's certainly not what we want to have. We have already accommodated the 767 with 30 actual nickels, and of course we could have done silver dollars and that kind of stuff to make the change a little bit more efficient. So what we really want is the 767 minus the 750. The 750 coming from 30 times 25 for quarters. That's going to give us 17, and then we're going to say, okay, well, we want 1 dime, right? The 1 dime to accommodate the 10 cents. So now the question is, well, how do we actually do this computation? We could go back into our code and say, and let's reuse amount because we don't really need the initial amount anymore. We can say amount equals amount minus Q times 25. If we look at what we've done here, amount minus number of quarters times 25. The new amount will be 17. That's not actually the most efficient way to write this. Really what we've computed here is the remainder of the integer division. 767 divided by 25 is 30, remainder 17. And we already know how to do a remainder. So what we can do instead is just say amount mod 25. And that's a little cleaner. And we can see right off the bat that we don't use this Q variable. The only thing that's going to change for computing dimes and nickels is just going to be the denomination. So continuing on, for nickels, the dimes is going to be the amount divided by 10. And so we can continue to go and calculate nickels. We're going to do the same thing. We're going to get the remainder. So we're going to say amount is equal to amount mod 10. Back over here, we would have the 17 minus 10. And that's the remainder. For nickels, it's going to be a similar approach. N equals amount divided by 5. Amount is equal to amount mod 5, the remainder. Seven minus the individual 5 will give us 2. And this is just going to be equal to the number of pennies. And we actually can go back into our code and we can remove that separate variable. If I wrote it there, yeah. We don't even need this. So let's print out everything. We'll print out dimes. Nickels. And pennies. And we'll just use the amount variable, which has the remainder already in it. Remember, the user just sees the labels, not the actual variable that's being printed out. Okay, so when we run this, when we type in the 767, we see we've got the 30 quarters to get us to $7.50. We see the 1 dime to add the 10 cents, so that's $7.60. We see the nickel to get us to $7.65, and then finally the 2 pennies to bring us the rest of the way up to 767. If we run it again with another number, 113, again we see the desired output, 4 quarters to get us to $1, a dime, and then 3 pennies to bring us to the $1.13. Okay, so far so good. The output looks good. The program works. However, most people don't think of paying for things in cents. We think about dollars and cents. So what we'd like to do is change the input strategy for the user, so the user can type in, instead of 1,156 cents, they can just type in something like $11.56. So we'll have to read in doubles. And what we can do is when we read in a double, just like when we read in 7% in a previous programming example, and we changed it to be 0.07 so we could work with it easier, we could read in $11.56 and multiply by 100 to make it into an integer, 11.56 cents. So to do that, in our code, it's not too difficult. What we can do is we just maybe read in a double called input, and we'll read that in, and we'll make amount equal to input times 100. So when a user types in $7.67, 7.67, we'll multiply it, so we'll get 767.000, and we'll convert it into an integer by storing it into an int. So if I run this, and we rerun the program, we type in 767, we get the same answer as we had been seeing before. So we can see that there would be 30 quarters to $7.50, 1 dime to get us to $7.60, 1 nickel to get us to $7.65, and then 2 additional pennies. So let's give that a build. Oops, sorry about that. And rerun the program, $7.67, and we get the same numbers we got before. Now let's read in, or let's test it with our other input. We'll type in the $1.13. And suddenly we see an issue. $1.13, when we entered it in as 113, an actual integer, it came back as 4 quarters, a dime, and 3 pennies, which was correct. Now all of a sudden, take the same code that worked for $7.67, perfectly fine, and it comes out as 4 quarters, 1 dime, but only 2 pennies. And this is a numerical problem that it happens for a few numbers, but it's something that's very tricky the first time you notice it. And it can be pretty perplexing as to why that's happening. So we look at that $1.13. Why is it that we're only getting 2 pennies back? Why aren't we getting the 3rd penny later on? We're printing out all the values. All the values are exactly the same each and every single time across. One thing that we can look at is, well, how did we convert this number back? How did we convert that $1.13? Did it end up being the $1.13 that we would expect? So right after this, whenever I find a strange bug, I print out any piece of data that I haven't printed out already, in hunt of the first variable that it really went wrong. So right after they type in input, I'm going to compute amount, and I'm also going to print it out. And I just want to make sure that that number is right, so I can understand exactly what went wrong. Because certainly this code down here, that worked for 767. It seems kind of odd that that wouldn't work for another number. So I'll type in the $1.13, and there's our problem. $1.13 for some reason got changed to, when I multiplied it by 100, got changed to 112. And that doesn't seem to make initial sense, but if we think about how numerics work a little bit more deeply, we can see that it does make a little bit of sense. $7.67, we can see actually was $7.67. So the question is, why isn't the computer able to multiply $1.13 times 100 and get 113, 113? The issue is not that it can't. The issue is really that this isn't exactly what we think it is. So when we do this with doubles, one of the things that we need to remember is that floating point numerics is a very different numbering system than regular integer binary numbers. So we think back to bits and bytes, right? And we know that the number of bits dedicated for a particular data type will tell you how precise those numbers can get. What we haven't really talked too much about is that IEEE standard for floating point notation. And it turns out that in a fixed bit notation, we can, off to a very, very high degree of significant digits, we can store most numbers fairly precisely. But there are a lot of numbers out there that aren't actually perfectly represented in 32 or 64 bits in floating point notation in binary. And 1.13 happens to just be one of them. There aren't a tremendous amount, but there's enough that you'll come across this problem. The computer actually stores 1.13 as 1.1299 and all the way out, many, many, many nines. So floats and doubles have a high degree of precision, but doesn't matter how much precision they have we can't actually represent this number. And it's the same issue as in a 10-base numbering system. You know that you can't represent 1/3 perfectly, right? If you write down 1/3, it's really 0.3333, and it goes out infinitely. 1.13 in a binary system turns out to be one of these infinitely repeated numbers like this. Now, that's generally not an issue. As we use 1.13 in numeric computations, the level of significant digits that we have reserved here is enough that we're never going to really run into a problem. We'll have enough precision. Ultimately, we would print this out and we would round when we print it. Cout will automatically round and we get 1.13. The issue here is that what we're doing is multiplying by 100. We are essentially taking a numeric floating point value up here, input. We're multiplying it by 100, which gives us a double of 112.99999. But then we're bringing it into an integer amount. That fundamentally changes the data type. And in fact, we actually got a warning in Visual Studio on this, a conversion from double to int, possible loss of data. When we multiply 1.12999 by 100, we get 112 point something. Casting that into an integer, as we've seen before, just removes the decimal places, and we get 112. So how do we correct this problem? It's a tricky problem to have. It's not all that common that we'll actually try to convert doubles into integers, but if we do, a general guideline for this is to take your double, multiply it by your 100 first, and then add some value less than 1. 0.5 makes the most sense, and that will make sure that whatever is out here, right, even if it's 0.01 or if it's, whatever that happens to be, if we add 0.5 to it, it'll cause this number to round up. Right? So it'll cause that eventual value to be 113.49999, and of course that 0.4999 will be removed. Again, if it was 112.001, that would be slightly different. As you add 0.5 to it, it'll be 112.50001, and it'll still be cut off to 112. So by choosing midway through that last numeric value or last integer, we ensure that we're going to round up. Only if this decimal place at the right-hand side of that decimal place is above 0.5 will that integer value get rounded up. So let's go back into the code and do that. And we should be careful to test all of the other ones that worked okay. So we can test 7.67 and see ourselves, yes, certainly that turns out okay. We can see the 1.13 now, and now we see that it did round. The 1.12 was 1.12999 that the user really entered when it got stored into variables, gets rounded up to the $1.13, and we get the right number. Now these kind of numeric problems, these are fairly rare, but in general, the change from double to int does crop up fairly regularly, and the compiler will give you warnings about it generally. And a compiler warns you about it because you certainly could end up with a problem that we saw in this last example. So this process is called essentially casting and promotion. C++, we've already talked a little bit about integer division. We know that C++ will perform mathematics only on like data types. So in order to do this, if you write down 5.0 divided by 2, C++ automatically promotes the lower ranking data type. Now what does lower ranking mean? It means a data type that can store a smaller range. So the lowest ranking data type would be bool because the range is only true or false. There's only 2 options. Coming up after that would be character. There's only 256 options within a character set. Integers and a 2 to 32. Float is a much larger range, and then double is the highest practical range that we have. So the promotion will always go up. And this, of course, is why 5 divided by 2, since they're integers, they just behave as integers, the result's 2. But why 5.0 will result in a promotion of 2 to 2.0 from an int to a float. We always promote up. And then 5.0 divided by 2.0 will be done in floating point arithmetic, and the value will be 2.5. If we want to cast downwards, generally not that great of an idea, but like we saw in the problem before, if the user types in a decimal number and I want to convert back to integers, I can. It's generally dangerous, but we can do it. Certainly data might be lost. 1.8, for instance, will become 1. If we need to do that, there's a special casting syntax to remove the compiler warnings. Compiler warnings are fine, but we generally don't like to have a lot of them floating around. They generally indicate a problem with the program. So it's sort of a good practice to, if you're purposely doing some casting like this, to cast a double into an int, it's a good idea to formally cast it so the compiler does not throw warnings. And that way you don't get used to sort of just ignoring warnings. 3 ways of doing this. One is to assign the double. In all cases, I'm going to take this double and I'm going to assign it to an integer. One way I can do that is with this parenthetical notation. I put the data type, the destination data type, this double, y equals 5.5. I'm casting it to an int. Another style sort of looks the same but a little bit different. It's called the functional style, where we put the variable or the number, 5.5 could have been put in here as well, that's going to be cast to an int. The newer way, the more modern approach, a little bit more verbose, is to do a static cast. And this has some slight implementation differences that are beyond the scope of what we're covering right now, but this is the recommended style. Static underscore cast is a keyword, followed by these angle brackets and the destination type. So to get rid of my compiler warning, if I switch over to Visual Studio, we can see that compiler warning down here. Let's rebuild actually. We can see that compiler warning right down there. To remove that, I can put this entire expression for my amount in parentheses and do static cast int. And if I make things a little smaller so we can see it better, it certainly is a little bit more verbose. That actually is kind of a good thing because it attracts our attention. We realize we're doing something that's potentially a little bit dangerous. Dangerous in that we might not get the results we want. And certainly there's no difference between the output here. And now we don't have the compiler warning.